Hi there, this video is going to walk you through the Euler rule for contours of functions of x and y, which, as you're aware, is the style of function that we tend to encounter in thermodynamics. Okay, so what we're going to do is consider our function, we'll just call it a general function, f of x and y, where the total differential for the function is given by df equals a dx plus b dy. Okay, so you could picture that as a state space, like we've done before, where we've got our f of x and y, and we have our y dimension and our x dimension. Okay, so again, like we are familiar with from working with our other state spaces, we know that A is essentially df dx at constant y, and B is df dy at constant x. Okay, so what we're going to do here is say we want to know something about how x changes with y at constant f. Okay, so there's a number of ways that we can express this quantity verbally. Okay, so one way to say that is we want to know something about the path on a contour of our function. How does x change with y along a contour of our function? Or we could say it like we're walking along a contour of a particular state space. Okay, so here we're just kind of traveling along our state space where x and y are both changing. Okay, so some of these phrases will make more sense when you're thinking about them in the context of looking at a state space like we do here, or in some of our CGIs. Okay, so might be seeming a little bit kind of abstract right now, but again, you will work with these kinds of kind of traveling on contours as we move through some of our exercises. Okay, so again, we're looking at a total differential of the form df equals a dx plus b dy. Okay, and we said we want dx dy at constant f. All right, so to get there, we're going to apply the derivative across the entire total differential. Okay, so this is similar to what we did in the total differential for enthalpy video. All right, so we want to have df dy at constant f equals a dx dy at constant f plus b dy dy at constant f. And these are partial derivatives, just to be clear. Okay. Now we apply our no-brainers. Okay, so our no-brainers, remember, are we have change in f with respect to y at constant f. That quantity is going to be 0. And then we're looking for anything else that we can simplify. So I'm spotting this dy at constant f. I see that, and I know that that's going to go to 1. Okay, so what does that leave us with? Well, we've got a dx dy at f equals minus b, and then we want to have dx dy at f as our final result. So again, just simplifying things a bit, we end up with dx dy at f equals minus b over a. Okay, so we could also write that in terms of the differentials that are represented by those b and a coefficients. So could also say That's just the change in f with respect to y at constant x over the change in f with respect to x at constant y. Okay, so remember, these types of expressions have physical meanings for us. Okay, so again, thinking back to our constant volume heat capacity or internal pressure, okay, those are the types of quantities that tend to be represented by these sorts of expressions. Okay, so let's do an example with a function that we're familiar with now. So again, working with our total differential expression for enthalpy. So one version that we have for our expression for enthalpy is dH equals Cp dt plus mu T dP. Okay, again, remember that's similar to our du equals Cv dt plus pi T dV. Okay, so we are looking for, let's say we want the expression dt dP at constant H, so we want to know how does the temperature change with respect to pressure at constant enthalpy. Okay, this quantity is also known as the Joule-Thomson coefficient, okay, which is given by the symbol mu jt or just simply mu. Okay, so this is to distinguish it from the mu sub t that we have up here. So different mu, okay? And I'll make that note, not ut. Okay, they're related, but they're not equal. But we'll see how they're related in just a second. Okay, so just like before, we're going to apply that derivative across the entire total differential expression. So everything essentially gets differentiated with respect to p at constant h. So we end up with dh dp constant h equals cp dt dp at constant h plus mu t dp dp at constant h. Okay, so hopefully at this point you can recognize that you want to apply your no-brainers. Okay, so at this point we want to hopefully start recognizing some of those quantities that are going to allow us to simplify our expression a bit. Okay, so again, we're going to have no change in enthalpy at constant enthalpy. We know that that one's going to go to 0. Okay, and then we have, again, that quantity where we essentially have unity. Okay, that's going to go to 1. And then we can simplify our remaining terms. So we have Cp dt dP at h equals minus mu t. Okay, so this is just like what we did a few minutes ago. Okay, except now we have some more meaningful thermodynamic quantities to. All right, so we were interested in this quantity, T dP at constant h. So let's rearrange so that we have that quantity. And we end up with minus mu t over Cp. Okay, so just like before, we know that these symbols represent differential quantities. Okay, so we know that mu sub t is essentially just dH dP at constant t. And then our Cp is dH dt at constant p. All right, and then just to finish it up, we know that that is equal to our Joule-Thomson coefficient. All right, so we can measure this in the lab. All right, and we'll play around with that a bit in class. So another way to write this kind of macroscopically is this is essentially just your change in temperature over your change in pressure. So what the Joule-Thomson coefficient tells us is essentially how does the temperature change as we change the pressure of our system. And this is applicable most directly to expanding gases. Okay, so depending on your gas and the temperature that you start your expansion at, some gases will cool upon expansion and some gases will heat up upon expansion. Okay, and this is actually how we get gases compressed. Okay, we do Joule-Thomson Joule-Thomson expansions, and that cooling gas will allow us to essentially liquefy gases. All right, so again, just to bring home the point of the relationship between mu t and our Joule-Thomson coefficient, we can see that they're related by our constant pressure heat capacity. And what's neat about this is that if that mu t quantity is greater than 0, then that tells us our temperature is going to go up. And if it ends up being less than 0, our temperature is going to go down. All right, so you'll have some practice working with these quantities in your homework and looking a little bit more closely at that Joule-Thomson coefficient. All right, hope this was helpful. Thank you.